Imagine trying to trap a miniature burning star inside a metal box without it dying or vaporizing the cage. Current nuclear power relies on fission, splitting heavy atoms like uranium, which leaves behind long-lived radioactive waste. Fusion does the opposite. By forcing two light hydrogen atoms together, it releases a massive wave of energy and leaves nothing behind but harmless helium. This chart tracks atmospheric carbon dioxide and annual emissions since 1750. Look at the blue line tracking CO2 emissions. The rate doubles approximately every 30 years. We need a carbon-free baseline energy source to halt that climb. Solar and wind are essential, but their intermittency means they require backup. To replace carbon-heavy plants entirely, we have to build machines capable of sustaining this stellar reaction. In December 2022, we reached a major milestone. Inside the National Ignition Facility, scientists pointed 192 lasers at a capsule the size of a BB. This graph shows the energy exchange of that shot. They fired 2.05 megajoules of laser energy into the target and produced 3.15 megajoules of fusion energy out. For the first time, a laboratory achieved ignition, getting more energy from the reaction than was put in to start it. The reaction lasted only a fraction of a second, but it confirmed the fundamental physics. The discovery transformed fusion from a theoretical goal into a massive engineering race to build a machine that can power a city. The National Ignition Facility uses lasers as a sledgehammer, crushing a fuel capsule to create a violent inward shockwave. This pressure overcomes the Coulomb barrier, the natural force causing positively charged nuclei to repel. Only a massive implosion pushes them close enough to fuse. Scaling this is a hurdle. A power plant must shoot and clear these targets thousands of times a minute, without failure. While lasers proved the physics of ignition is possible, that mechanical repetition is why many engineers are looking for a different way to hold the plasma, magnetic force. These are the most complex machines ever designed. If you're learning something new about how they work, please hit like and subscribe to keep exploring these breakthroughs with us. This approach is called magnetic confinement. Because no physical material can survive contact with 100 million degree plasma, scientists use magnetic fields to build an invisible bottle. The most common design is a hollow donut called a tokamak. Tokamaks have been the workhorses of 20th century research. They were developed originally in the Soviet Union and have served as the baseline for global experiments for decades. But the tokamak design faces the Greenwald limit. The Greenwald limit is a threshold where plasma becomes unstable as its density increases. Just as the plasma becomes dense enough to generate power, it can suffer a disruption that breaches the magnetic field. A commercial plant cannot risk these instabilities damaging the reactor. Because the traditional donut shape is prone to these sudden losses of control, researchers are turning to a more complex geometry. This is the stellarator. By twisting the donut into a complex asymmetrical ribbon, the machine stabilizes the plasma without needing the dangerous internal currents found in a tokamak. We've known this design for years, but calculating the exact coil shape was too difficult for humans. Modern supercomputers changed the strategy. Using machine learning, engineers can now computationally design and identify stable geometries that were previously impossible to visualize. This modeling has turned the stellarator into a viable contender. By removing the limits of human calculation, we can now design reactors that are inherently stable, shifting the focus toward the final engineering challenge. We are no longer debating whether fusion is physically possible. The focus has moved to a commercial race, determining which machine design can be scaled to the grid the fastest. While building these experimental facilities cost billions, that investment is small compared to the cost of our current energy system. We lose trillions of dollars every year to the environmental and social impacts of carbon emissions. Think back to the Wright brothers at Kitty Hawk. That first flight only lasted seconds, but it demonstrated that powered, controlled flight was a reality. Fusion is now in that same transitional phase. We have proven the reaction is controllable in the lab. The engineering race to build the first commercial power plant has officially begun.